Hello everyone, I am Karan Mashru. Welcome to this video. In this video, we are going to discuss solution of the problem of the day, that is AVL tree deletion. Also in this video, let's keep a target of 100 likes. So if you are watching this video and if you like the solution, make sure you hit that like button. Also, this problem is of hard level, but I have tried to explain it in as much detail as possible. So even if you do not have much knowledge about AVL trees, or if you do not have the required background, if you watch the complete video, you will definitely get the solution. First of all, let us start by understanding the question. Okay, so what does question say? Given an AVL tree and n values to be deleted from the tree, write a function to delete a given value from the tree. All the n values which needs to be deleted are passed one by one as input data by driver code itself. You are asked to return the root of the modified tree after deleting the value. So basically we are given an built up AVL tree and we need to delete n values from it. Now these n values will also be selected by the driver code itself, will be handled by the driver code itself, and they will be passed to the delete function. Okay, we just need to delete that value and make the required changes, and then return the modified root of the modified AVL tree. Okay, so first of all, let us start by understanding some basics. So first of all, let us discuss some things about an AVL tree. So what is an AVL tree? It is nothing but a self-balancing binary search tree. Now what does self-balancing binary search tree means? First of all, what is binary search tree? Binary search tree is a binary tree in which the value of a particular node is greater than all the nodes in its left subtree and less than all the nodes in its right subtree, and this holds true for all the nodes. Okay, that is binary search tree. So basically, suppose this value is 100, then on the right hand side of it I can have values only greater than 100. So this is suppose 105, right? Then suppose here it is 107. Now what here I want to place a value, it should be less than 105 because it is on the left hand side of 105, but it is on this subtree is on the right hand side of 100, so it should be greater than 100. So something like 103, right? Then here the value should be less than 100, so it can be 90. Here the value should be less than 100 as well as less than 90, so because it is on the left part of the 90 as well, so something like 80. Here the value can be here the value should be greater than 90, but it should be less than 100 because it on the left hand side of because this subtree is on the left hand side of 100, so something like 96 and so on. Here what you can say, here the value should be less than 96 but greater than 90, so something like 92 is valid. So this is basically a binary search tree, which is a binary tree, and for all the nodes two conditions hold true, that for each and every node the value in the in all the nodes in the left subtree is less than that node, and the value in the nodes in the right subtree is greater than that node. Okay, so for example, for 100 all these values are greater and all these values are less. For 105 this is less, this is more. For 90 these two values are more, this value is less. So this is binary search tree. Now what does self-balancing binary search tree mean? Self-balancing binary search tree means for all nodes the height of the left subtree minus height of the right subtree modulus should be less than equal to 1. For all the nodes, the difference between the height of the left subtree and right subtree cannot be more than 1. Now understand this. Suppose this is 100, this is 90, this is 80, this is 70, this is 60, this is 50. Now is it a binary search tree? Yes. Why? Because it is a binary tree. All the nodes can have at max 2 children, so this is a binary tree. Is this binary search tree? Yes. Why? Because if we look at for 100, all the values in its left subtree are less and all the values on its right subtree should be more, but there is no right subtree. For 90, all the values on its left are less. Similarly for 80, 70, 60 and 50, right? But if we look at this, then the height of this is basically n, right? If there are n nodes, the height of this is n, right? So if we are using tree, then if we can reduce the height of the tree, then our searching insertion may become easier. Okay, now if we need to traverse all the n nodes to find the value 50, then there is no such use. So there comes the introduction of AVL trees, which is self-balancing binary search trees. So the left subtree height and right subtree height for all the nodes should be less than equal to 1. Now if I calculate the left subtree height, then it is how much? 1, 2, 3, 4 and 5. So it is 5, and in the right subtree there are no nodes, so 5 minus 0 is 5, right? So it is, you know, kind of tilted on the one side. So this condition should hold true. So it is a binary search tree with this condition hold true for all the nodes. Now let's read the question further. So now if we go through the question further, then let's have a look at first example. So this is a self-balancing binary search tree. This is an AVL tree. We can see the height of left subtree minus right subtree for any node is not more than 1. So here we want to delete 4. So after deleting 4, okay, sorry, the total number of values to be deleted are 4, okay, and they are 4, 1, 3, 6. So after deleting 4, the tree has rebalanced itself and 5 has come here, and 6, 7 are here only, and 2, 1, 3 are also as it is, but this 5 has come here and 4 has been removed, and this also holds true that the height of the left subtree minus height of the right subtree absolute value is less than equal to 1, right, for all the nodes. Okay, then value to be deleted is 1. Next value, this is to be deleted, so we have removed it, still the condition holds true. Then the value to be deleted is 3. We deleted 3, still the condition holds true. And then the value to be deleted is 6, and we have deleted 6, and 7 came above. Okay, so basically after each and every deletion, what should happen is, again the height of left subtree minus height of right subtree, that is the difference between height of left and right subtree for all the nodes, should not exceed 1. So it should remain balanced. Okay, so that is basically what we need to do. So we need to delete a node as well as rebalance the tree. Okay, so complete the function delete node, which takes root of the tree and the value of the node to be deleted as input parameters, and return the roots of the modified tree. Okay, and then there is a note that tree will be checked after each deletion. If it violates the property of balanced binary search tree, an error will be printed followed by the in order traversal of the tree at that moment. If instead all the deletion are successful, in order traversal will be printed. If every single node is deleted from the tree, null will be printed. The expected time complexity is height of the tree, and expected auxiliary space is also height of the tree, and constraints are given here. So now we know about AVL trees, right? AVL trees are nothing but self-balancing binary search trees. Means they should follow the property of binary search trees, as well as they should be balanced at all the points of time. Balanced means the height of the left subtree minus height of the right subtree for all the nodes should be less than equal to 1 at all the given point of time. So after each deletion, the tree should balance itself, right, such that this condition holds true. So basically, in the process of deletion of a node in an AVL tree, it is basically in two steps. First is deletion of node same as binary search tree deletion, right? So a node is deleted the same way as we do in a binary search tree. And second is rebalancing the tree, right, because it is an AVL tree. So now first of all, let us understand how we do a deletion in a binary search tree. So this is a binary search tree, and we are given first we want to delete 12 and we want to delete 10. Okay, so these are two different operations. We will apply it on this only, right? So these two are independent operations. So first of all, I want to delete 12. So how does deletion in binary search tree occur? In binary search tree, whenever we want to delete a node, we replace that node with, exchange that node's value with its in order successor or in order predecessor, and keep doing this recursively until it goes into the leaf node and then delete it. Okay, so basically we replace that node's value with its in order successor or in order predecessor. So what does this mean? It basically means that this is the value which comes after that node. So suppose I want to delete 12. So this is the value which comes after 12 in the in order traversal, and this is the value which comes before 12 in the in order traversal. What is an in order traversal of a binary tree? In order traversal of a binary tree is when you visit the left subtree first, then the root node, and then the right subtree, right? And when you do in order traversal of a binary search tree, you get the values in the ascending order. So if I apply in order traversal on this, the output would be 7, 8, 9, 10, 11, 12, 13 and 15. The output would be 7, 8, 9, 10, 11, 12, 13 and 15. This would be the output. So basically for 12 the in order successor is which one? The in order successor is 13 and in order predecessor is nothing but 11. So we replace 12 with either of these values, and whenever 12 reaches the leaf node we delete it. So basically suppose I replace it with 11, so 11 will come here, 12 will come here, 12 will become the leaf node and delete it. So what I'll get? I'll get 10, I'll get 9, I'll get 11, I'll get 15, I'll get 13, right? And this 7 and 8 would remain as it is, right? And 12 would come here, but as it would be the leaf node, I'll delete it. Is this still a binary search tree? Yes. That's why we replace the value which is to be deleted with its in order successor or predecessor, because it still maintains the property of a binary search tree. We replaced it with 11. Suppose we replaced it with 13, right? So 12 will come here, 13 will go here. Now 13 will go here, 12 will become leaf node, will delete it. 13 is here, it is greater than 10, 15 is greater than 13, it is on the right hand side, 11 is less than 13, it is on the left hand side. That would also hold the properties of binary search tree. Okay, you can do any of them. Suppose I want to delete 10. So what I'll do, what is the in order predecessor of 10? It is 9. 9 comes just before 10 in the in order traversal. So how can we find this while implementation? The in order predecessor is the largest value in the left subtree. So in order predecessor is the largest value in the left subtree. Why? Because in order predecessor is the value which comes just before it in the in order traversal, right? Just before it means it should be smaller than that, and just before it means it should be as large as possible. So it is the largest value in the left subtree of the given node. Okay, we can find it in that way during implementation. And for the in order successor, it is the smallest value in the right hand side subtree, because right hand side subtree contains all the large values than the current node, and we want just a value which is just after that. So the smallest value in the right hand side subtree of the given node. So suppose I replace 10 with 9. Okay, so 10 will come here, 9 will go here, right? So this will become 9, this will become 12, this will become 15, this will be 11, this will be 13. These things will stay as it is. 10 will come here, right? So 10 will come here, and 7 will be here, and 8 will be here. But we keep doing this recursively until 10 doesn't come to the leaf node. 10 is not a leaf node. So again I'll see the in order predecessor. Which is it? The largest value in the left subtree. Okay, just a mistake. So basically 8 is here, right? So the largest value in the left subtree is 8. So I'll replace 10 with 8. So this will come here, right? I'll rub it out, and the 10 will come here, right? Now this is the leaf node, so I'll delete it. So what will happen? I'll delete this part, so I'll get this. Is this the binary search tree? Yes. 9, these values are greater than 9, these values are less than 9, this also holds the true, and this also holds true for binary search tree. So this is basically how we do deletion in binary search tree. We replace the value with its in order or successor or predecessor, and keep doing it recursively until it comes to the leaf node, and then delete it, and the binary search tree is still maintained. Now let's look at how we will do rebalancing. So now after we make deletions in binary search tree, it might happen that the or in an AVL tree, it might happen that the height of one left subtree minus right subtree may go beyond 1. Okay, the absolute value of that. Now there is a term called balancing factor. Okay, balancing factor. For each node this should be -1, 0 or 1. What is balancing factor? It is nothing but the height of the left subtree minus height of the right subtree. For each node, if it is 0, it means both the heights are same. If it is -1, it means the height of the right subtree is 1 more, because this is nothing but height of the left subtree minus height of the right subtree, right? And if it is 1, it means that the left subtree height is 1 more than the right subtree. But if it is anything else than this, then it means that now the tree is disturbed by the deletion and it needs rebalancing. So it may happen. Okay, so for example, here T1, T2, T3 and T4 are understand, T1, T2, T3 and T4 are subtrees. T1, T2, T3 and T4 are subtrees. Okay, they are not single nodes. Okay, so what happens is sometime after deletion of the node, the height may change. Okay, so let us take one example here. Okay, so suppose I delete 11 here. So now at present, is it a AVL tree? Let us calculate balancing factor for all the nodes. For this, the balancing factor is 0. Left subtree minus right subtree, both height is 0, so this is 0. Here there is no left subtree, here there is 1, so 0 minus 1 is minus 1. Here left subtree has how many? 2 nodes, and here there are no nodes. Okay, suppose I add one value 9.5 here. Okay, so here there are 2 nodes and 2 minus 1 is what? 1. So its balancing factor is 1. What is the balancing factor of this? 0. What is the balancing factor of this? 0. What is the balancing factor of this? 1 minus 0, that is 1. What is the balancing factor of this? 0. What is the balancing factor of this? Height of the left subtree 1 minus height of the right subtree 2, that is minus 1. What is the balancing factor of this? Height of the left subtree 1, 2, 3. Height of the right subtree 1, 2, 3. 3 minus 3 is 0. So all the values are between 0, 1 and minus 1. So it is an AVL tree because it is balanced. Now suppose I tell delete 11. So if I delete 11, it is a leaf node, I'll directly delete it. So suppose I delete it, right? Now if I look at this, what is the balancing factor of this? There is no node here, so 0 minus 2. So this is the height of the right subtree is 2. So this becomes minus 2. So now the tree is imbalanced and it needs balancing. Okay, so this is the case where we need to think about balancing. Now there can be 4 different cases. Okay, now suppose after deletion the left subtree height minus right subtree height is, so basically the balancing factor is greater than 1. Okay, suppose the balancing factor is greater than 1, it means the height of the left subtree minus height of the right subtree is greater than 1. So why? So this subtree is more, so let y be the child of that. Okay, so I am taking this one sub part of the whole tree. Now suppose for y, the child with the y is balanced. Okay, z is not balanced because I am looking from the point of view of z. The height of the left subtree minus height of the right subtree is greater than 1. All the other nodes are balanced. Now suppose for y the balancing factor is, greater than or equal to 0, but it is balanced. It means either it is 1 or 0, which means that height of the left subtree minus height of the right subtree is 0, both are same, or height of the left subtree minus height of the right subtree is 1, which means the height of the left subtree is 1 more than the right. So wherever it is more, I am calling it x. Is this much clear? So starting with the unbalanced node, this is the unbalanced node, right? I am first marking y as the child which has more height. So here this has more height, here this has more height, here this has more height, and here this right subtree has more height. Then I am marking x as the node which has more height and which is a child of y. So here it is x. Here it is x on the right hand side, here also x is on the right hand side, and here x is on the left hand side, right? Now one question may arise that y is a balanced node. It means that its balancing factor is 1, minus 1 or 0. Suppose it is 0, that suppose y balancing factor is 0. It means that height of the left subtree and right subtree both are same. So in that case, how will we decide x? For z, height of the left subtree and right subtree cannot be same because it is imbalanced, but y is balanced, it has balancing, so it can have balancing factor 0. So if it is 0, how we will decide x? So what we will do is, see, whenever the balancing factor is 0, then x would be in the same direction as y was with respect to z. So here y was on the left hand side of z, x is also on the left hand side of z when balancing factor is greater than or equal to 0. Now if the y is on the left hand side of z and x is on the right hand side of y, this will be the case when the balancing factor for z is definitely greater than 1 because height of the left subtree is more than the right subtree, and balancing factor for y will be how much? It will be definitely -1. So basically a height of this minus height of this subtree should be -1. At that time only we will select x on the right hand side. If it is 0 or 1, we will select x on the left hand side. Similarly here y is on the right hand side, so the balancing factor for z would be how much? It would be less than -1 because height of the left subtree minus height of the right subtree should be less than -1, only then it can be imbalanced. And x is also on the right hand side when the balancing factor of y should be less than or equal to 0, so it should be either 0 or -1. Okay, if the balance here, what is the case? Balancing factor is less than -1 and balancing factor of y is equals to 1. It is 1, so left subtree has one height more than the right subtree, so we are selecting x on the left hand side. So I hope you are clear with the selection of y and x. Whenever a node is imbalanced, that is the balancing factor is not 1, -1 or 0, we select y as the subtree node which has larger height, and we select x as one of the child of y which is also having larger length. So for example here this part is having more length, so x is selected on the right hand side. Okay, and whenever there is a tie for both the children of y, that is the balancing factor is same, it should be in the same direction as y is in z. So here it is left, here it is also left, here it also right. If the balancing factor is 0, we will take x on the right hand side only. Okay, and t1, t2, t3, t4 are subtrees. So this is basically called left case. Okay, this is left and again on the left hand side y, z and x. This is called left right case. So this is left, this is right, this is called right case, and this is called right left case. Okay, this is right and this is left. Now there are different steps to balance them. If you have left case, you just do a right rotation. So what does right rotation means? It means that you take the node which is imbalanced and rotate it on the right hand side. Now understand this, what will happen? Y will become the parent node, z would become the right hand side child of y. So y would become the parent node, z would become the right hand child of y. Is this much clear? Now understand one thing. Now we will keep these things as it is. So this x will remain as it is, T3 will remain as it is, T4 will remain as it is. Okay, and T1 will remain as it is. But now we cannot place T2 on the right hand side of y because y on the right hand side of y we have z. So where is the place empty? If we look clearly, the left child of z was y, but now there is no left child of z. So this place is empty. Can we place T2 here? Yes, definitely. Why? Because T2 is less than z. Yes, it is less than z. It is on the left hand side. It still satisfies the property of binary search tree. It should be on the right hand side of y. It is still on the right hand side of y. And other things we have not changed only. So basically in the right rotation, what we do? We take y here, z here, and we take T2 as the left child of z. Why? Because the left child of z is now free. The right child of y is now busy because now we are occupying z there, and so and T2 satisfies the condition to be here. Now this became balanced, right? Because here the balancing factor was greater than 1. Okay, so now we need to keep repeating this process up till we reach the node. Okay, we will see it in the next slide, but this tree will become balanced. Okay, now this is the case when this is left right case. So y is on the left, x is on the right of y. Okay, so in this what we need is we need a left rotation on Y first and then a right rotation on Z. So what will happen when you do left rotation on Y? So pick Y and rotate it on the left. So X will go up. So what will happen? X will go up, then Y will come here, right? Then T4 will come here. X will go up, Y will become its right child. T2 will still be the left child of Y. And now there is no place for T3, and Y right hand child is also not there because first it was X. So we will place T3 at here. It should be greater than Y. Yes, it is on the right hand side of it. It should be on the left hand side of X. It is on the left hand side of X. So, and the other thing remains the same, Z and T1. So this will be Z, this will be T1. Now we need to do a right rotation. So what will happen is basically we will do right rotation on Z. So X will go up. What will happen is X will go up, Z will come on the downside, T1 will go here, T1 will go here. So X will go up, Z will come down, T1 will go here. Now there is no place for T4, but the left child of Z is empty. So T4 will come here. Then we will have Y here, and then we will have T2 here, and then we will have T3 here, and this will be a balanced tree. Okay, so now these are the two cases we have seen. Now let's see the other two cases. So for this case I have erased the middle part, and then this is the final answer I have wrote here. And now let's look at these two quickly. So this is the right case where Y is on the right hand side of Z and X is on the right hand side of Y. Here for left case, what we did a right rotation. Simply same here we will do a left rotation on what? We will do a left rotation on Z. So Y will go up. So Y will go up, Z will go on the left hand side, T1 will come here. Now T2, that is the left child of Y, will be acting as the right child of Z. So here the T2 will come, then X will be here, T3 would be here, and T4 would be here, and now this will become balanced. Okay, so this much subtree would become balanced in all these cases. Okay, understand, we might need to go further until the root, and we might need to go further to the ancestors. Okay, they might get unbalanced in this process. We will see it in the next slide. Now let's look at the last case where it is right left case. Here in the left right case we did left rotation on Y and right rotation on Z. Here we will do right rotation on Y followed by a left rotation on Z. So right rotation on Y, X will go here. Okay, so Z will come here, X will come here, Y will go here, T2 will be here. Then what will happen? X will go there, Y will go there, T2 will go there, T1 will be here only. And now for the right child of X will become the left child of Y. So T4 will become here. It is less than Y, but it is greater than X, and T3 will remain here only. Now we will do a left rotation on Z. So X will come here. Okay, so what will happen? X will come here, Z will become the left child of it, T1 will become here, Y will remain here only, T2 will remain here only. Then T3, that is the left child of Z, X will become the right child of Z. So T3 will become here and T4 will come here. Again this subtree is balanced. So these are the four different cases. Now one more thing which I want to discuss is that we need to check for balance recursively until root is reached. So what is the example? This is an AVL tree. Okay, you can calculate the balancing factor for each node. It would be either 0, -1 or +1. Okay, now suppose I am asked to delete 101. It is the leaf node, I'll delete it. Okay, so what we will do is we will delete 101, right? So we deleted it, but now if we check for this node, so what we will do is we will keep going towards its ancestor, and whenever we find an unbalanced node we will rebalance it. So now 102 is not balanced, Why? Because the balancing factor of 102 is what? Left minus right. It is -2. So it is not balanced. Which case is this? Right, right. So we need to do a left rotation. So what will happen? 104 will come here, 102 will come here, and 105 will come here, because we will do a left rotation and this 105 will go. Okay, so let's remove this. Now if you look carefully, this node balancing factor from -2, it became 0. So this is balanced, but this became unbalanced. Why? Calculate its balancing factor. What is the height of the left child? 1, 2, 3, 4. So balancing factor is 4 minus 1, 2. It is 2. Now what is this case? It is left. Y will be this, and this has greater height, so x would be this. So it is left right condition. So I need to do a left rotation on y. So 92 will come here, 90 will go here, and the whole arrangement will change. Then I'll do the whole right rotation and it will become balanced, right? So the basic point of this was that whenever you do rebalancing, whenever you delete a node, okay, so first of all, in binary search tree deletion, what we were doing? So in deletion in binary search tree, we were recursively exchanging the values with in-order successor or predecessor until it becomes the leaf node. Once it becomes the leaf node, we used to delete that value. Now we will traverse back again through the ancestors, and in each step we will check the balancing factor. If it is not -1, 0 or 1, we will check one of the following 4 cases, and according to that we will adjust it, make the rotations as required, and we will keep doing this until we go to the root. Because as we saw in the last slide, while making the balancing factor of one node proper, that is 0, -1 or 1, its ancestor balancing factor might get disturbed, because basically what happened was the right hand side subtree height here was 3, but because we tried to balance this, it had decreased by 1 and it became 2. Now this was 4, so 4 minus 2 became 2. Initially the balancing factor for this was 1, 4 minus 3, but because we made changes here, this balancing factor was affected. So again we need to make changes. So just to conclude, what we will do is we will do deletion as per the binary search tree, replace the value with the in order successor or predecessor until we get to the leaf node, delete that node, come back, traverse back, do the backtracking, and each node check the balancing factor. If it is not -1, 0 or 1, check which case it is out of the 4 cases and do the rebalancing. Okay, also how we will reach to the node which we want to delete, because we have access only to the root node. See, AVL tree is also a balancing binary search tree. We have access to the root node, right? So if the value of this node is equal to the value which we want to delete, okay, work upon it. If it is not, if it is greater than what we require it, go to the left subtree, because if this value, this node's value is greater than what we need to delete, then the value which we want to delete will be in the left subtree, which has less values than this node. If the value of this node is less than what the value we want to delete, suppose k, then go to the right subtree and find the respective value. Okay, now let's look at its actual implementation. So now let's look at the actual implementation. So basically we need to complete this function where the root of the AVL tree is given and the data which we need to delete. Okay, so first of all, if we will recursively look for the data. So if root data is equals to data, then what we will do? Else if root data is greater than data, so if the current node value is greater than what we require, then what we will do is we will call the delete node function in the left subtree. So we will part root left and we'll pass the same data which we are looking for. Okay, and suppose there is some modification done in the left subtree, because it might happen that the rebalancing is required. So what we will do is we will return the new head of that left subtree and we will store it into root left. Okay, because the there might be some rotation happened. Okay, so ultimately this will return, this function will return what? Ultimately it will return back the root of the AVL tree after the changes done to the main function. Okay, So here, and similarly, if the root data is not equal to data and it is not greater than data, that it means that the data in this node is less than the data which we are finding. So in that case, we will call this function on the right subtree, and we will store the head of the modified right subtree in case if it is modified in root right. Okay. Now if it is equal to data, we will check if it is leaf node. So if root left equals to null and root right equals to null, then simply free that root. So free that memory and make root equals to null. Okay. Else if root left is equals to null, it means that there is no left subtree. So in that case, we only have the right subtree. It means that in that case, we can only find the in order successor. So what I have done is I have taken one temporary node pointer, and I have tried to find out the in order successor. So the smallest value on the right subtree. What is in order successor? The smallest value in the right hand side subtree of that node. So I have passed the right hand side subtree pointer root right, and this will find the smallest value in that. We will look at this function later, and it will return it in the temp value. Now I have got in order successor in this. So what I'll do is I'll swap that value with the current node value. That is what we do in the deletion binary search tree. Now we recursively call the deletion, right? So root right is equals to delete node root right, and the value would be what? Temp data. Remember, we replace that value with the in order successor. Now we will recursively call deletion for the in order successor. So what is the in order successor? What is that value? So now it has gone to that. Okay. So for example, suppose this is 10, this is 12, this is 13, and this is, let's say, 11, right? And I want to delete this. So first of all, I'll find the in order successor. It is 11, so I'll swap the value. So this is 11 and this is 10, but 10 is still there now. I want to delete it. So I have swapped the value in temporary data. Temporary data was before what? 11. Now it has become 10, and the root data was 10. It has become 11, but I still want to delete this now. So what I'll do, I'll call the recursively this delete node function on the right hand side subtree of this, that is the right hand side subtree of this, and the value which I want to delete is temp data, that is 10, right? So that is what I am doing. Else, so if left subtree is not null, then I am searching for the in order predecessor. Okay. So similarly, I will find the in order predecessor in the left hand side subtree, and I'll swap the value, and then I'll call the recursively the root left, the left hand side subtree, and I'll call for this value, that find this value and delete it. So it will keep on calling recursively until this value goes to the leaf node, and then when it goes to the leaf node, this if part would be executed. It will free that value and it will make it equals to null. Okay, so this much is complete. If root is equals to null, if there was only one value and we deleted it, then we'll simply return that root. Okay, now let's look further. So basically we have exchanged the value recursively with the in order successor or predecessor until that goes to the leaf node and then deleted it, right? Now comes the rebalancing part. So what we have done is, first of all, I have calculated the left hand side subtree height. So LH is equals to get height of the left hand side subtree, and RH, that is the right hand side subtree height, is equals to get height on the right hand side subtree. So now the new value of the current root would be what? Root height is equals to 1 plus max of left hand side subtree height and right hand side subtree height. We need to keep updating it because it might change. Now the balancing factor is get balancing factor of this root. So it will basically do the left hand side height minus right hand side height. Okay, if balancing factor is greater than 1, okay, and balancing factor of root left is greater than equal to 0. What does this mean? Understand, if balancing factor is greater than 1 and balancing factor of root left, if balancing factor is greater than 1, it means y is on the left hand side. These, okay, these two are the cases. Balancing factor is greater than 1, and if balancing factor of root left, that is y, is greater than equal to 0, this is the left case. if it is equal to -1, then it is left right case. So that is basically what we are looking here. Understand, if balancing factor is greater than 1 and get balancing factor, so basically balance factor of root left is nothing but y, which we saw in that example. Is why it would be on the root left? Because the balancing factor of z, that is the node which is imbalanced, is greater than 1. So if this is also greater than equal to 0, it would be left case. Else if balancing factor is greater than 1, and no need to mention this balancing factor is -1, that is the only remaining case, then it is what? So this is left case, this is left right case. If balancing factor is less than -1 and get balancing factor of this is less than equal to 0. If balancing factor is less than -1, so y would be on the right hand side, and if balancing factor of root right, that is y, is less than equal to 0, then it is right case. Otherwise, if this balancing factor of y is 1, then it is right left case. Okay, so if balancing factor is less than -1 and balancing factor of root right is less than equal to 0, this would be right case, and otherwise it would be right left case. So if it is left case, just do the right rotation on the root and store the new head into the root. If it is left right case, do the left rotation on the left subtree. So root left is equal to left rotation on root left, that is nothing but y. So in this case, do left rotation on y, that is the left subtree of the node which is imbalanced, left rotation on y, and then right rotation on z. So left rotation on root left, store it in root left, and right rotation on root and store it in root. Similarly in RR case, do left rotation on the root, and similarly in RL case, do right rotation on this right side subtree, and then do left rotation on the root, and then finally return the root. Now let's look at these different functions which are used here. So now let's look at this function from bottom to top. So in order predecessor, what is that? In order predecessor is the largest value. It is basically the value which comes just before that in the in order traversal. So it is the largest value on the left hand side subtree of a node. Okay, so what we will do, it is the largest value on the left hand side subtree. So for example, if a subtree is 10, let's say 9, for let's say here it would be 18, and so on. Here is the tree, and here is also a tree. Okay, so now I want in order predecessor of this, so it is the largest value on the left hand side of it, right? So what I'll do is I'll call the in order predecessor function and pass in this node pointer. Okay, so what it will do is it will keep on going towards the right hand side, because for that subtree I want the largest value. So if root right is not null, go on the right hand side. If root right is on the null, then the current value is the largest. So for example, it is like this: 10, 9, 8, 7, and so on. So the in order predecessor is this itself, because there is no large value than this, because there is no right hand side. Okay, so we will directly return root if root right is null, otherwise we'll go on the right hand side. Similarly for in order successor, it is the smallest value on the right hand side subtree. So we will pass pointer of the right hand side subtree and will keep moving on the left hand side. So if root left is null, then return this value, otherwise go on the left hand side. Okay, this is get balancing factor. So if the pointer is null, balancing factor is 0, otherwise get height of the left subtree minus get height of the right subtree, that is the balancing factor. This is the get height function. If it is null, then height is 0, otherwise return the height of that node. Okay, now let's see other functions. So now two functions are left, that is the right rotation and left rotation. These are the two most important to understand. Okay, so we'll look at the right rotation. So suppose this is the case. In this case we do right rotation on the z, so y comes on top and it gets balanced. So if we look at here, basically root is nothing but z. Okay, so root is nothing but z. Then I have taken y is equals to root left. Obviously this is y, and x is equal to y left. So x is equals to y left. Now understand this: root left is equals to y right, root left is equals to y right. So basically you understand this, what we were doing when y goes up and z comes on the right hand side of y, there was no position to keep t2. So what we did was we placed t2 on the left hand side of z. So that is what they are doing. Root left is equals to y right. So this is the root left is equals to y right Okay, so t1 is as it is. Now look further. Y right is equals to root, because we were doing right rotation, so root becomes on the right hand side of y. So y right is equals to root. So y right is equals to root. This x will remain as it is, t3 will remain as it is, and t4 will remain as it is. Okay, and root height, now this will be changed. The height of this can change, right? So sorry, y right will become what? It will become to root. Now root height will change, so we will change the root height if it is changed. So because z was here, it height was what? 1 2 3. But now if we look at it, the height is here, it is 1, and here it is also 1. So height will change, so we will take max of this and this, and y height will also change. Height of this will change and this will change. So we will say y height is equals to 1 plus max get height of this and get height of this. Get height of root, because root is on the right hand side and x was on the left hand side, right? And for root height will be decided by what? Root left and root right only. Okay, and then we will return y. Why we will return y? Because now y is the new head of this subtree, right? Before now there would be a big tree. Okay, this is only a part of it. So its ancestor would be pointing to z, but now they should point to what? Y. So now this is the new head. Similarly, you can draw an example where z, y, x, t1, t2, t3, t4, and you can run this left rotation function on your own on this, and you'll understand this how all the things are adjusted like we looked here. Okay, so now if we talk about the time complexity, what would be the time complexity? It would be big of, see, understand, first of all, whenever we want to delete a node, we will find that node. Okay, we will traverse the tree, we will either go towards the left or right until we find that node. So basically it would be height of the tree, right? So it is basically height of tree. Once we find that node, we will take it to the leaf node. So if we totally calculate, we went from the root node to the leaf node, okay, by exchanging it with in order successor or predecessor recursively. So that is height of the tree. Then what we will do, we will backtrack, and at each step we will check the balancing factor of each node, okay, each of the ancestor. So again we will go from leaf node to the root node. So again we will traverse how much? Height of tree, right? But we will do rebalancing also at each step is required. Rebalancing takes how many steps? 1 or 2 steps. So I can multiply it with 2, right? And this process is repeated for how many times? It is repeated for, this whole process is repeated for n number of times, because totally we want to delete n nodes. So now 3 times height of tree is nothing but height of tree, right? We do not consider constant, so it is basically n into height of tree. Okay, here the expected time complexity is given height of tree, but it is when only one deletion is required. When there are n deletions, the total would be n times height of tree. Okay, so this would be the total time complexity. If we talk about the time complexity of one delete function, it will be height of tree. Okay, and what would be the auxiliary space? The auxiliary space would be how much? Big O of, see, we are taking only a few variables, okay, to use. We are not taking any array or something, so we are not occupying any space in that way, but we are calling recursively functions, okay, to find that node to be deleted, then replacing it with in order successor and predecessor. So we are basically calling recursive functions. And how many recursive functions will be maximum called? Maximum, it would be height of the tree, right? Because whenever we are traversing left, right, we will keep traversing until we do not reach the leaf node, and all those recursive function information will get gathered up into the stack, which handle the recursive functions details. Okay, so the height of this stack, it will occupy memory as much as height of the tree. okay, this auxiliary stack. So that would be the auxiliary space, the size of this stack, and that would be big O of height of tree, because that many recursive functions can be called recursively. Okay, so I hope you have understood this. Now let's submit this code. Let's submit it. So we have solved this question successfully. I hope you have understood the solution completely. Thank you.